In 10.6, we learned how to solve equations that have roots in them. So once you learn how to solve equations, you usually anticipate that probably the next section of the book is going to be word problems. And yeah, in a sense, 10.7 here is kind of word problems, but it's not really word problems. The word problems here are not really very challenging. The word problemness of the word problems here is fairly minor. Pretty much everything we do in 10.7 here has to do with the Pythagorean theorem, which we've talked about before. When you have a right triangle, the two shorter sides, a squared plus b squared, add up to the longer side squared. So that's a familiar rule. The reason this shows up here in chapter 10 is if you're trying to figure out a or b or c, if you're trying to solve this thing, you're going to have to take a square root at some point, and chapter 10 is where we learn how to do stuff with roots. So let's apply this Pythagorean theorem thing to this word problem here. We've got a room. It's 17 by 23, so it's 17 one way, 23 the other, rectangular room. We're trying to run a wire from one corner over to the other corner, and there's two choices for how we could do that. We could do it sort of the low-tech, boring way of just going down one wall and along the other wall and attaching it to the baseboards down in the corner of the wall or something. Or there's this shortcut where you go straight diagonally from one corner to the other. And we don't know what that distance is yet. I'm just going to call it d for distance. But look, if you draw that picture up, it's not hard to figure out how to draw the picture. And look, there's a right triangle in that picture. So what we're going to do is plug those numbers in to the Pythagorean theorem. Make sure that the long side is always isolated. That's the, two small things add up to a big thing. So the big number has to be over on the side by itself. And then you grab your calculator and you start pressing buttons, because nobody here is going to know what 17 squared is right off the top of their head. It is 289. And 23 squared, same thing. Who memorizes that kind of thing? 23 squared, that's 529. And you add those up. 289 and 529 is 818. So d is the square root of 818. And that's not a particularly nice square root. That's why we had to wait till chapter 10. Notice what the directions are telling you here. It says, give an exact answer. But wait a sec. Give an exact answer for what? Don't lose track of what the problem actually said. This happens to me all the time. I'm sure it happens to you too. You get so involved in the actual nitty-gritty of the mathematics and the algebra of what you're doing that when you get to something like this, you feel like you've answered the question, and maybe you've completely lost track of what the question was. Here, the question was, how much wire could you save by going diagonally? This is not the amount of wire you would save if you went diagonally. The amount of wire you would save is what the long distance was gonna be minus what we figured out the short distance actually is. So the long distance, 17 plus 23, that was gonna be 40 feet of wire. And now the shorter distance is 818. This is how much wire you would save. How much were you going to use? How much did you actually use? What was the difference? So make sure when you think you're done with a problem, read the problem one more time, just in case. Everybody makes mistakes by losing track of that. So if they want an exact answer, here in chapter 10, this is the answer. We just have to simplify it. So you take a look at that square root of 818. You say, okay, 18, that means 9 goes into it. Nope, sorry, 9 does not go into 818. And you keep doing that. You keep looking for perfect squares, like maybe 25 goes in. No, 25 doesn't go in. How about 49? No, that doesn't go in. And eventually you're forced to accept the fact that 818, that's not going to simplify any. We're kind of stuck. If they want an exact answer, there is your exact answer. We will save 40 minus square root of 18 feet of wire. That's not a very practical answer, though. That doesn't really tell me, is that a lot of wire? Is this expensive? I don't know. So there is also in this question, this part of the answer we're supposed to provide. It says, and 1 rounded to the nearest inch. Because practically speaking, I want to grab my calculator and figure out what number that actually is. So you grab your calculator and you go 40 minus square root of 818, and you see what it gives you. Calculator says, let's see, 11.399300071, etc. That's not quite what the question wanted either. Notice this little word here. This, right now, that number, that's feet. So we got to turn that into inches. We got to take that, multiply by 12, and get 136.7916, blah, 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 inches. And if we're rounding to the nearest inch, that's 137 inches. I don't know if I'm happy with that answer. I mean, technically, it answers what the question is telling me to answer. But when I think of 137 inches, my brain can't help but say, okay, how many feet and how many inches? You know, that's like 10, 11 feet and, let's see, 137 minus 11 times 12 is 5 inches. So 11 feet, 5 inches. That's kind of a better answer. I kind of like that one better because it feels more meaningful. That's a lot of wire. You know, that's almost 12 feet of wire. That if the wire's something expensive, like I don't know, some high-end speaker wire or something, that might save me quite a few bucks. So this is an example of the kind of word problem you're going to run into here. The word probleminess of it is not particularly challenging, except don't just race through the math and think you're done. Stop when you think you're done and see if you've really answered the question. There may be some more steps. There are a few extra little special things that this section 10.7 does. For example, we're going to take a look at some special case right triangles, and once we understand how these work, it's going to produce some rules. There are going to be some special shortcuts. So, first of all, the two special cases are situations where you have not just a right angle down in the corner, but the other two angles are either 45 and 45 like this, or 30 and 60 like that, because these have nice little symmetry properties that make them even easier than normal to figure out. For example, if these angles are both 45 degrees, then this triangle is sort of a mirror image this way, diagonally. And what that means is, whatever measurement you have there, you got to have the same measurement here. So instead of talking about a squared plus b squared equals c squared, here you have x squared plus x squared equals c squared. And if you solve that, to figure out what c is, you get a very easy number for this diagonal. It's whatever x was, times the square root of 2. So if you know one side, without getting the whole Pythagorean theorem out, you can fill in all three sides. Like, that's 7, and this is also 7, and this is 7 root 2. Lickety-split, you're done. Now, over here for this one, things are a little more complicated. You have to think of both this 30, 60, 90 right triangle up here, and sort of its reflection down underneath. This reflection would also, of course, have 60 degrees there. It would also have 30 degrees there. And the most important thing to note is 30 plus 30, isn't that 60? And then look at the whole giant triangle, which has got 60 degrees up there, and 60 degrees over here, and 60 degrees over here. All three angles are the same for that big triangle. Here's what that means. If this measurement here is x, actually I've just used x, let me use a different letter. Let's say if this measurement here is a, well, a mixes up with the Pythagorean theorem. Let me use y. There we go. If this measurement is y, from here to here, then this is a mirror image down here. This is y, which means this entire side on the left is 2y. And for this big triangle, since it's all 60, 60, 60 all the way around, if this is 2y, then so is that. That's also 2y. And then we use the Pythagorean theorem to figure out this third side here. Y squared plus b squared equals 2y squared. 2y squared. Square that out, you get 4y squared. Subtract y squared, you got b squared equals 3y squared. Take your root. And this third side down here is y times the square root of 3. So again, this means if somebody were to just tell you like this here is 19, then this is 38, and this is 19 times square root of 3, once you know this side here, finding the other sides is a matter of moments. In fact, if they tell you like this long hypotenuse here is 10, you can sort of backtrack and say, well, if that's 10, this over here has to be 5, and if that's 10 and 5, this is 5 root 3. So this is a shortcut to get to your answers without using the Pythagorean theorem. And based on what we've just worked out there, these are the rules you end up getting. These are the proportions if your angles are 45 and 45. These are the proportions if your angles are 30 and 60. Okay, we're almost done. Just a few more things related to the Pythagorean theorem. One of these things is something called the distance formula. And this, I think, is a really good example to teach people why it's important to know the reasons behind a thing rather than just memorizing the formula. Because I could just say, this is the distance formula, memorize it, and it would be really intimidating because it's a very messy looking formula. But if you back up and talk about where the formula comes from, it's not as intimidating as it looks. So what we're trying to do here is we're trying to build a formula for the distance from one point to another point. So when I'm all done here, I'm going to have some formula in here. Distance equals something involving the coordinates of the points. So it's going to have an x1 and a y1 and an x2 and a y2 in it. And here's how we simplify this. Think of those 2 points using something we talked about back in Algebra 1 that doesn't seem like it would be relevant at first. Think of those 2 points and their slope. Remember rise over run, slope? Well, the rise is this vertical distance here. And the rise is the difference between the y-coordinates. It's whatever the height is up at the top point minus the height down at the bottom point. That's how you figure out what the rise is. If it goes from a height of 7 to a height of 10, then it rose 3, that sort of thing. And you do a similar thing for the run. How far did it go left to right? Well, it's the new horizontal position here, which is x2, minus the original horizontal position there, x1. So the run would be x2 minus x1. Normally, when you're talking slope, you make a fraction. You go rise over run. But this time, look at the picture we've got here, and you'll recognize, hey, wait a sec, this thing's a right triangle. I can take the green and the red and the blue here, and I can plug them all into the Pythagorean theorem. I can plug them into a squared plus b squared equals c squared, and maybe that'll go somewhere. So a is x2 minus x1. B is y2 minus y1. And c, well, c is the easy part. C is just d, the distance we're trying to figure out. So if you want to know the formula for the distance, we've kind of almost got it right there. We just got to get rid of that exponent, and based on what we've been doing today, you know how to get rid of that exponent. Just take a big old fat root. So if I were to have told you in the beginning, this is the formula for distance, the distance formula is this giant messy monstrosity, you probably would have panicked. Your brain would have just shut down. You would have said, oh, hell no, and you wouldn't even been able to remember it. But if you back up and look at the picture, and you think about rise and run, a couple of fairly simple ideas, and you feed them fairly easily into the Pythagorean theorem, you end up creating this formula, and it's not really as bad as it looks. One other formula for today, and then we'll be done. And this is, notice I put quotes on the word formula. This is a situation where I'm not even sure the word formula applies. It's too easy. What we're talking about is a formula to figure out the coordinates of this point here in the middle between 2 other points. So it's going to be a formula that you plug things in and it'll give you the x-coordinate and the y-coordinate. And really, I'm not even going to use the Pythagorean theorem here. I'm just going to sort of break it down into a concept. The word midpoint means the point halfway in between. I mean, that's just sort of vocabulary. What does it mean when somebody says this? You know, if I said the midpoint was over here, you'd say, no, that's not the midpoint. It's not halfway in between. Midpoint has to be halfway in between. So what that means is the x-coordinate has to be halfway in between. So this will be half between the x's. And the same thing for the y-coordinate. This y-coordinate here will be half between the y's. And here's the thing. You already know how to find halfway between a couple of different numbers. Like if I said this x-coordinate over here was 10, and that x-coordinate over there was 22, you know, say that's 10, comma, something, and this is 22, comma, something, and I say, what's halfway between 10 and 22? There's this thing you do, and you've got a word for that thing. Halfway between 10 and 22, you're finding the average. The middle point between two numbers is the average. So if what you're doing here is finding an x-coordinate that's halfway between the x-coordinates, what you're going to do is the regular formula for average. You're going to take those x-coordinates, add them up, and divide by 2. And if you're going to do the same thing for the y's, you're going to find a y-coordinate that's halfway between the y-coordinates you're starting with. You're going to add them up and divide by 2. So instead of a formula, it's really more of a vocabulary word. Just remember that the formula for midpoints is to take the average. Just average the points. Average the x's, and that's your x-coordinate. Average the y's, and that's the y-coordinate. So what does this have to do with Chapter 10? Why is this here, and does it have to do with roots? The only reason it's in Chapter 10 is because it's kind of closely related to the distance formula, and so it kind of just tagged along for free. So yeah, it's not related to roots, it's not related to the Pythagorean theorem, and it's a pretty simple idea that just shows up here in this part of the book.